All right, in this module, or in this lecture series here, let's look at different types of solution phase reactions. And the first one that we have is precipitation reactions. Most ionic molecules tend to be soluble in water, but not all are. To generate a solid precipitate, this would be a solid that is falling out of solution this is known as a precipitation reaction. So to generate a solid precipitate from mixing two homogeneous solutions is a precipitation reaction. We already looked at one. We looked at, in an earlier example in this module, sodium chloride reacting with mercurous nitrate to produce sodium nitrate and solid mercurous chloride. And so there is our precipitate. And so this is a precipitation reaction as a result. A common example that is really just very, very colorful is looking at potassium iodide react with lead nitrate, or in this case plumbous nitrate, to produce potassium nitrate that's aqueous, and then a solid product with the lead namely the lead iodide solid. And so here again we have the solid precipitate. And this one is a bright yellow color. Here's an example demo of making lead iodide using a precipitation reaction. So check out the trippy colors with this demo. So here you have the two solutions above. You see a straw which has the potassium nitrate. It's going to drop right into the potassium iodide. As soon as we see that, ooh, cool colors evolve. That is the lead iodide precipitate. So two solutions above potassium iodide, below lead nitrate, they come into contact, boom, solid precipitate. We can observe the color, we can observe the heterogeneous solution creating or being created, and it's pretty cool looking as well given that bright yellow color for the lead iodide. So here a very visual, simple example of a precipitation reaction with the lead and the iodide combining to produce solid yellow lead iodide. There, are ways to predict the formation of a solid precipitate. And this is really based on the metal and non-metal or polyatomic combinations. So if we go to our textbook, we have a table in the text that relates these ideas. And so here's a table that talks about two different things. Ions that are generally soluble, and then we have, ions that are, not generally soluble or generally insoluble. And so what I would do is just try to look at one part of the table. If you know one half of the table, then by default you should know the other half of the table. So if we start at the top, we have compounds that are generally soluble, and then if we go to the right of that, we see we have exceptions. So here, notice that we have a lot of these, group 1 ions, or group 1, A ions, and notice that there are no exceptions, right? So remembering like lithium, sodium, potassium, and ammonium is good, because now you know that it's always soluble, it's always aqueous. Two other polyatomics that we see here, then the next level would be nitrate and acetate. And again, we have no exceptions for them. So these are great ways of getting, ionic molecules into solution, is to make sure that, if you're looking at the metal, like, oh, I always want to pair that metal with nitrate or acetate, and it'll always be soluble. We have halides here, but realize that there are some exceptions to the rules as we see it. And so we have to be careful of, these ions, such as silver, mercurous or Hg2 plus 2, and lead plus 2, because then all of a sudden these molecules are insoluble. And then lastly, we have sulfate. And it has some exceptions as well. A lot of these being plus 2 compounds, or plus 2 metals, with strontium, barium, lead, and calcium. And then silver is in there as well. So notice that lead is a common exception. It's an exception for the halides. It's also some exception for the sulfate, and similarly with the silver. So if you know those groups are all soluble, then you have these other groups down below, such as, hydroxide and sulfide. And these tend to be very insoluble, and you might be like, well, wait a minute, I'm used to sodium hydroxide and potassium hydroxide. Well, right, notice that those are exceptions, right? That when we have those ions paired, right now we have something that is soluble. So, and notice that that's really the first part of the table, right? That lithium, sodium, potassium, ammonium, there are no exceptions. They're always soluble. So that's why sodium hydroxide is very soluble. It's because of that, that one partner, the sodium. And then we have, some other examples with the sulfides. Notice that we have, some group 2 metals for the sulfide, as well as for the hydroxide. They're pretty much the same in terms of this idea of soluble or slightly soluble. And then at the bottom we have carbonate and phosphate. And so again, we see the same ions that we did before, right, as far as these exceptions for now things that are soluble. So that's why I would, when looking at this this table, right, is, just, know the top half of the table. And you'll know, the bottom by default. The other thing is you only need 1/2 of the ionic molecule to be soluble for the entire molecule to be soluble. So all you have to do is find one of them, and then we have this idea of solubility. So let's look at an example of utilizing this table. And we could use this example of ferric chloride plus sodium hydroxide produces what, right? So we have to be able to predict the products that we are producing. So step one is basically to split the molecules into their ions. So we would have, this iron plus 3, plus we would have 3 chlorides. We would then have our sodium in the +1 state, and then our hydroxide in the -1. Once we split the molecules into their ions, the second step is to change partners. Right? Do-si-do. So the iron and the chloride were originally paired with one another. Now we should pair the iron and the hydroxide with one another. And the chloride was paired with the iron originally, so now let's pair it with the sodium that we have. And so if we just start to now predict the products, right, and that's really all we're doing here, is that we're changing partners to predict the possible products. We would end up with iron hydroxide as one of those products. Now we should now be careful with our stoichiometry, right? Iron is in the +3 state, hydroxide is -1, so there'd have to be a 3 of them, of those hydroxides there. So we would need to maybe change the stoichiometry above and put that 3 in front of the hydroxide in step 1. And then the other possible product would be sodium chloride. Now that's 1-to-1, and we do have 3 chlorides from the ferric chloride, so eventually we're going to have to add this 3 as well to make sure the sodiums are balanced. So we could say that we're making, sodium chloride, and really there's actually 3 of them there, right? So these are the possible products that we have. And then what we want to do is predict Are they aqueous or are they solids? And if we go to our sodium chloride, we would have something that's aqueous. Sodium is a group, the 1A, right? Remember, there's no exceptions. Halides tend to be soluble as well, but it's paired with a group 1A metal, so that's definitely going to be very soluble. And if we look at the ferric hydroxide, we find that hydroxides are insoluble. And so that's why we would predict that we have a solid ferric hydroxide. So that's the reaction. We actually get a solid product, and that's actually telling us that we have a reaction. If everything was stayed aqueous, well, then there's actually no reaction happening at all because everything would stay in its ion dissolved form. But the fact that we're making something new, and we know that because of this solid precipitate that's falling out of solution, we now have a chemical reaction. We now specifically have a precipitation reaction. So that leads to step 3, which is, basically to write the total ionic reaction. The total ionic reaction includes all of the ions present in the reaction, as well as, solid and aqueous products. So if we write the whole reaction now, we would say that I have iron plus 3, it's aqueous. I have those 3 hydroxides, each one minus 1, that's aqueous. I have 3 of those sodium ions. And I have 3 of those chloride anions. And that is going to produce, and I apologize, I should, I put these all together, this is fine. I mean, realize that we really had started with ferric chloride, right, and sodium and the sodium hydroxide. But we end up with ferric hydroxide as our solid product. And then we also have, 3 of these sodium ions as well as 3 of the chloride anions that are still aqueous. So that is the total ionic reaction, writing all of the materials there. And then finally, in the fourth, step, depending on what the question is asking, we write the net ionic reaction. And the net ionic reaction only represents the ions and the solid precipitate for, the actual precipitation reaction that's taking place. You kind of have 2 different entities, right? You have the spectators, which are the ions that are just watching the game. they're, you know, ions. Ions that do not change. From that idea of going from starting material to product. And then we have the players. And these are the ions combining to produce the solid precipitate. So if we look above, right, for our spectators, these ions that are, you know, watching the game, that would be our sodium and our chloride, because they remain unchanged. And then we have, you know, the ions combining to produce the solid. And so that's our iron and our hydroxide to produce our solid material. That's where we see the actual change. So we have, you know, the idea of the players, and we have the idea of the spectators. Spectators are watching the game, players are playing the game. So in terms of that net ionic reaction, we would just write, you know, the iron plus 3 reacting with the 3 hydroxides to produce solid ferric hydroxide. And that's usually how we end it. So that's the idea. You just have to break it down into those individual steps to develop the total ionic reaction, as well as then developing the net ionic reaction. So do one more example. So here we want to write the total and net ionic reactions for the following reaction. We have calcium bromide plus silver nitrate produces what? So if we do our first step, right? First step is to, you know, represent all as our ions. So we have the calcium plus 2. We have the 2 bromides. We have our silver plus 1. And we have our nitrate minus 1. We basically, you know, swap metals. You know, do-si-do, and then predict products and phase of those products. So we would want to pair, you know, the calcium now with the nitrate, and we would want to pair the bromide with the silver as far as the do-si-do goes. So that means we would have as a product calcium nitrate. We would have to make sure that we had 2 of those nitrates because of the charge. Calcium is plus 2, the nitrate is minus 1, so we need to have that balancing of charge, so we're going to need a 2 in front of the nitrate. And then our other product is going to be silver bromide. They are on a 1-to-1 level since they both have the +1, -1 charge. So that means we need a 2 in front of the silver, which makes sense with the nitrate, since those two are coming together as starting materials. So if we look and predict, we see nitrate, right? This is always soluble. There's no exceptions. So that means we would predict this to be aqueous. And then we have halides tend to be soluble unless paired with lead +2, mercurous ion +2, and silver +1. And so there we see the silver +1. That's our exception. And so as a result of that exception, we're going to see it as a solid product. And so there's our reaction. There's our precipitation reaction. So our total ionic reaction would then be, let's see, we had the calcium and the bromides reacting with now the silver nitrate. We're changing the stoichiometry from what we were seeing in the prediction step. And we get calcium nitrate and silver bromide as our products. Calcium nitrate is aqueous, silver bromide is solid, so that allows us now to then write our net ionic reaction, which would just show those ions that are reacting, namely the silver, the bromide, to make silver bromide. And notice that we're just at the most simplest state here. So even though above we see those 2's in front of the silver and the bromine, that's because of the calcium and just the balancing of that particular reaction, for the total setup. Here we just have these ones, silver +1, bromine -1. So it's just a 1-to-1 feature here. And so there is our net ionic reaction. So that's the idea of precipitation reactions. Here we've had a solid product in each case, but maybe you get 2 solid products. Also realize that the possibility is that you don't get any products. Maybe everything stays in solution. So keep that in mind. What I would do is practice these using the table in the beginning, trying to really focus on that top half of the table and get good at it. So that you can then transfer and practice some then without that table. You're going to need to be able to predict these types of reactions, and you will not have that table as a guide on an exam. So you need to have some predictive power with this particular type of process, the precipitation reaction process. Another type of ionic reaction is acid-base reactions. And we should have a definition of what an acid is. And for right now, we're being very general. An acid, is a molecule that donates H plus to the solution. H plus is also known as a proton. If we think about the hydrogen atom, it just has one electron and one proton, no neutrons. And so if we lose an electron to make a positive hydrogen, like we see here, that means that the only thing left is the proton, right? The electron is left because it's now positively charged. And so technically it is an actual proton. Another way to write protons, I'm not going to highlight this too much in this particular module, is that when a proton goes into solution, it actually reacts with water to make what's known as the hydronium ion. So, H plus is really saying the same thing as H3O plus. For right now, I think I'm just going to keep it simple with just the H plus idea. We have lots of different examples of acid. Hydrochloric acid, for example. When we put hydrochloric acid into water, it dissociates just like we would expect any metal or alkali metal chloride. And so that's why, this is an acid, is because of that, generation of H plus. Hydrochloric acid is actually a very strong acid, which is why it's a one-way reaction, or complete dissociation. Right? Remember, our ionics like to dissociate, so it'll completely dissociate into H plus and Cl minus. Another example would be, maybe on the weaker side, would be a common component to vinegar, which is acetic acid. And acetic acid, when we put it into water, actually isn't a complete dissociation. We still have our H plus that's generated, and then we have the rest of the molecule, the acetate, also, but this is basically a two-way street, meaning that not all of it ionizes. Some of that ionized product actually comes back to form the starting material. This is known as an equilibrium. It's a bit early yet for us to be getting into equilibria, but here's at least a brief introduction about it. So again, we're talking about acetic acid. It is an acid. It does, look at the generation of H plus. It's just a weak acid. And the weak acids we tend to notice have the two-way street arrows, the equilibrium arrows. Or equilibrium, and there is not complete dissociation. We kind of saw that with the electrolytes, right? The non-electrolytic solutions and the electrolytic solutions. We had one of those examples in the middle was acetic acid, and it was a very weak light, right? Because it was weakly ionic. And so we're seeing that here in terms of, yes, it does produce ions in solution, but it isn't complete like we have for something that's strong. So we have complete dissociation with that nature of the strong acid. For the weak acid, it's just simply not complete dissociation. That's all. We also have, on the flip side of that, then bases. And a base is simply a source of hydroxide in solution. So remember OH minus, this is one of these polyatomics that we utilize, and sodium hydroxide, which is a solid. If we put it into water, we generate sodium plus 1, and then hydroxide minus 1. So there's our example of a base. This is an example of a strong base, kind of similar to the acids. It's a one-way ticket, and there is complete dissociation. We also have weak bases as well. Ammonia is a weak base. And just like our weak acids, we find that these are now equilibrium-driven processes where the ammonia actually accepts a proton from water and then generates hydroxide. So we have that idea that in both cases we need to generate OH. So we see that here in our solid starting material for the sodium hydroxide, and we also see that it's not as obvious, but we do see the fact that this molecule generates hydroxide. So again, this would be a base, a weak base, but a base nonetheless. So with the weak base, we have really the equilibrium, two-way street, and again, this is not complete dissociation because of the back and forth that we have with the equilibrium. So those are some examples of acids and bases, and they're very reactive with one another. And the reaction that is involved with acids and bases is known as the neutralization reaction. So the neutralization reaction involves an acid and base starting materials that produce H2O as a product. There's also a salt product too. So in the easiest way to look at the neutralization reaction is just simply, okay, here's our acid, here's our base, and they both want to react with one another to make H2O. And so there is our neutralization reaction. And so notice now on the right side we are talking about something that is neutral. We have lost the charges of H plus and OH minus. So this is an example of like the base concept of a neutralization reaction. Let's look at an example or two of these types of reactions. So hydrochloric acid plus sodium hydroxide produces what? And so this is very similar to the precipitation, reaction, where, one, represent the dissociation into ions for those starting materials. So if we look, we would have, for the hydrochloric acid, we would have H plus and Cl minus, both aqueous. For the sodium hydroxide, we would have sodium plus 1 and OH minus 1. And so those are our ions. And we now just want to kind of do the same thing. We want to predict products by, swapping partners. Or that, do-si-do idea. So we would be looking at, the combinations of, Cl and Na, as well as then H plus and OH minus in that swapping of partners. So we would have HOH, I guess you could write, plus NaCl. And really, HOH, of course, is H2O, right? So I'm just trying to show you, these ions actually coming together. And so while this is not a precipitate, it is a new molecule, right? We've generated a new molecule. And in the case of acids and bases, that new product is always going to be water, and that's always a result of acid-base chemistry and the neutralization reaction when we're reacting those two together. So for the total Ionic reaction, right, we're looking at, H plus, Cl minus, plus Na plus, and hydroxide, producing then H2O and sodium chloride, which is aqueous. So there's our total ionic reaction. We have here, the spectators. We see that with the sodium ion and the chloride anion, not really doing any chemistry here. Just kind of along for the ride. And then we have our players. Right, and that lets us to now describe the net ionic reaction, which is, you know, exactly what we had up there prior with the neutralization reaction, right? That very general reaction of H plus OH minus produces H2O. So that's the nature of these, you know, acid-base reactions. They're really just, again, ionic. So we're doing the exact same things that we did prior with the precipitation reaction. It's just in these types of reactions, acid-base reactions, we don't get a solid product, right? We get the production of water as a result of an acid being neutralized by a base. Titrations is a method that utilizes acid-base neutralization reactions to basically quantitate an unknown concentration of a particular acidic or basic solution. So this is, you know, a method that we actually use, and so we have, you know, a couple of different terms within titrations. We have, you know, one term is the primary standard. Primary standard is basically, you know, a very pure molecule. You know, for which its mole value and molar value can be determined with good accuracy. So we often use a primary standard to really figure out something else. So it's a very pure molecule, which we can really know absolutely its mole value, subsequently its molar value, and this can be all determined with good accuracy. It's used to basically standardize other solutions. And standardize means like determining concentration. We then have a standardized solution and this is basically now an, you know, acidic or basic solution whose concentration is accurately known by basically application of the primary standard. So that's, the standardized solution is really called the titrant. Titrant is a strong acid or base to ensure quantitative or 100% reaction conversion. If your titrant equals an acid, then you are using it to basically figure out a base concentration. If your titrant is a base, then you're doing the opposite. You are using it to basically figure out an acid concentration. So that's the idea of the titrant. It's really, this standardized solution. We really, know its concentration. We know that already because of the primary standard that we've used to figure that out. And then we use this standardized solution. We use this titrant to then figure out an unknown concentration of the opposite, player. So, our titrant's an acid. We're figuring out a base. If our titrant's a base, we're trying to figure out an acid. We have the analyte, which is the acid or base of unknown concentration. And so those are really the three components. Really the most, the two that we are going to see a lot are the titrant or standardized solution, as well as the analyte, or analyte, however you want to pronounce that. Some other things that we have within a titration, we have what's known as the equivalence point. The equivalence point is the place during a titration where basically the moles of the titrant equal moles of the analyte. And if we think about it a little bit differently, we could simply say this is when moles of H plus is equal to moles of OH minus. Right? That's the equivalence point. It doesn't matter, what's the titrant or what's the analyte. Right? We're trying to figure out one, whether that be H plus or OH minus, but always what's going to happen is we're going to reach an equivalence point during a titration, and that's when our moles are equal to moles, right? And basically, these are starting materials. So both of these are what you could maybe call the limiting reagent, right? We're now on a one-to-one basis. This piece is probably the most important. and going forward, understanding that equivalence point idea. Some other terms that we have are endpoint. This is, simply when the titration is finished. This is when you have, excess of the titrant. And then we also have an indicator. And an indicator is a molecular dye whose color is pH dependent. This basically allows for a visualization of the equivalence point. And so that's important as well, right? That we have to be able to see, when we have, moles equal to moles. And while, we're going to get a lot more into acid-base chemistry in the second half of general chemistry, here we have to just realize that, okay, that there's going to be a color change, and then that's going to ascribe to the actual equivalence point where I have moles equal to moles. As far as like a, way to visualize this type of experiment, we could look at something like this as far as an acid-base titration. So what we have above, this is known as a burette. And basically it has volume markings. So it's kind of like a graduated cylinder. So you can know how much of something you're added. This is also where the titrant is. So here our titrant in this particular example would be hydroxide. So here is our titrant in this example. And then down here would be, all right, the analyte, what we're trying to figure out. And so what we do is slowly, as you can see, in going from one level, we were at the very top here. If we look at that burette on the left, our liquid amount was right here, and now we're down to here. So we've added a volume of this hydroxide has been added. And so as we're adding this hydroxide, we have a chemical reaction that is actually occurring. Right here is our neutralization. And so as you can see down below, notice that the hydroxides that are falling into solution have one white sphere and one red sphere. And then we're seeing that H2O actually being formed. So if we kind of look at the different materials here, right, there's our hydroxide. Here is our proton. And then what we're making is our H2O. So those are the different players within the titration, and eventually we reach a spot where now everything has reacted, right? So now everything has gone over to H2O. They've reacted on a one-to-one basis. And also notice the indicator color change, right? Again, to indicate the equivalence point. So that's that indicator and idea. And so now from this idea of the volume, right, that we started like up here, we're here. So here is the volume of OH minus to reach equivalence point. And I now know, the volume of that hydroxide. I know the molarity of that hydroxide. So that means I know moles of OH minus. And at the equivalence point, right, that's when moles of hydroxide is equal to moles of H+. And so that's how I can figure out the actual solution concentration. It is based off of that notion of okay, if I know the concentration of one, I can relate it to the concentration of another because of this quantitative reaction known as the neutralization reaction. So it allows me to determine that. So that's the idea of a titration. Let's look at an example of a titration problem. So here's our question. In attempting to determine the acid content in a bottle of vinegar, it was found that 22.3 milliliters of 0.240 molar sodium hydroxide was required to just neutralize a 50 milliliter sample of vinegar. Calculate the molarity of the acetic acid in the bottle of vinegar. So the first thing that we need is we need our, our acid-base neutralization reaction. And we have our starting materials as far as, the sodium hydroxide is really the titrant, right? That's what we're trying to, or rather utilizing to figure out an unknown. And then the vinegar, or the acetic acid here, is the analyte. So those are the two materials. So if we write those down, right, and going forward, we just want to make sure that we, swap partners, right? If we look at our charges, going a little bit faster now with this idea, we have the sodium +1, we have the hydroxide -1, we have the proton that's +1, and then we have the acetate, which is -1. So if we just swap partners, we would get sodium acetate and H2O. Right, again, we're just swapping those cations and their respective anions to generate, the sodium acetate, which is really just the spectator here. And here is our, hydroxide. Here is our proton, right? And there is our water in that idea of our neutralization reaction. So we have our, our H plus, we have our OH minus, and those are reacting with one another. So this is just a chemical reaction now. So all we need to do is, once we have the acid-base neutralization reaction, is basically just set up the conversion process. If we look up at the top, we have some information. We know how much of the sodium hydroxide we've added. We also know the volume of the acetic acid, or the vinegar bottle, really. So we just need to bring those two concepts together. So we're asked to solve for the molarity of the acetic acid, and we're started with this 22.3 milliliters of sodium hydroxide. So this is just getting onto that multimole superhighway. So first thing we would want to do is get into moles of sodium hydroxide, and that's where we would use our concentration. Once we're there, we can get to then moles, using our stoichiometry from the reaction above. We can get to moles of the acetic acid. And then, because we know that we're in 50 milliliters, that allows us to get to our concentration. So, this is our, our final step. Our first step is getting into moles. Second step, then getting into moles of the other molecule, the analyte. So first getting into moles of, the titrant, and then getting into moles of what we're actually analyzing, the analyte, which is the acetic acid. So we could just now set that up as a conversion. So converting to our liter volume for the sodium hydroxide, and then using our molar value to convert out of the solution and into moles of our titrant. So we're into moles of sodium hydroxide, right, step 1. Step 2, looking at the stoichiometry above, it's 1 to 1. So for every 1 mole of sodium hydroxide, that requires 1 mole of acetic acid. So that's using step 2 to go between one molecule and another. And again, there's the mole-to-mole superhighway that we've been talking so much about. And then we have our final step, which is now getting back into concentration. We know our mole value of acetic acid, that's in the numerator. So now we just need to divide by the volume of that acetic acid solution. And when we do that whole process, we end up with a concentration of 0.108 molar acetic acid, right, in the vinegar bottle. Could have been slower or stepwise if you want. You could have stopped at the moles of acetic acid and then just done that as the last step, right? This third conversion, right? But here we can string it all in a row as well. So if you feel like you want to go stepwise, please do. Or if you feel more confident, you can then start to string this dimensional analysis together. So that's the nature of acid-base reactions. So in this chapter, in this module, we've seen 2 different types of reactions now in solution. 1 is precipitation reaction, and 2 acid-base reactions, neutralization reactions.